Hey, what's going on, y'all? Sean of MassWap Tutoring here. Today we are going to talk about the mean value theorem. So we're getting a little bit more into how we use calculus to determine how curves look and stuff like that, and how they're shaped and this and that. So it's first derivatives, second derivatives, which I've talked about in previous videos, but we're kind of getting into where we can kind of interpret rather a little bit more about what's going on. Um, with graphs and stuff like that. But anyhow, make sure you like this video. Make sure you subscribe to the channel if you're not already, and let's get into it. All right, so first of all, let's state what the mean value theorem says. It says the following. If a function is differentiable, in other words, that means that if a function has a derivative on the interval a, b, okay, there exists a number which we'll refer to as C, between A and B, such that the following, let me put a colon there, F prime of C. So in other words, the derivative at that point is equal to F of B minus F of A over B minus A. And this can also be written as follows: F of B minus F of A equals F prime of C times B minus A. All right, so let's look at this and let's see what this actually looks similar to. This says if a function is differentiable, that means if a function has a derivative on the interval a, b. In other words, if the derivative exists, then there exists a number C, which is somewhere between A and B, such that when you take the derivative at that number, at that location, then it's going to be equal to the function at b at x equals b minus the function at x equals a over b minus a. And like I said, this is another way that it can be written. Now, what does this look like? This looks like an average. So um you have like for example, an average, or it even looks like a slope. Y2 minus Y1 over X2 minus X1. That's what it is. So it's a slope, it's an average, okay? So, and then of course, like I say, by cross multiplying, you can rewrite it this way. The function at B minus the function at A is going to be equal to the derivative, or essentially kind of like the slope times the x values. Okay. So this looks a whole lot like slope. And as a matter of fact, let's draw this here. So if you have the following, you have a function that looks kind of like this. Draw it as best as I can. Okay, so let's say this is x equals A, x equals B. Let's change the color. And so you have a point here, and this function goes like so. Okay. So you're going to have, this is point A, and has the coordinates A and then F of A. This is point B, and it has the coordinates B and then F of B. Then you have a point P. Okay. P is located at x equals C, as we were talking about up here. What color I want to do this? Let's do a blue, and I'm going to try my best to do a blue line. Okay, and so what you have here is, and I'm going to write the coordinates to that in a second, but you have some line, and this is not going to be perfect, y'all. Just kind of understand. Let me see. Let me change that color to blue. It's not perfect. I should probably move my P over a bit, but P is a value such that the derivative or the slope, in other words, let me get my red back. This is located at C and F of C, right? So the slope at this point is represented by this line here. And so what we are saying is that there is a point in between A and B where if you take the slope here, it's equal to, see if I can duplicate this line. Okay, we're going to take that. Okay, it's not perfect, but it's equal to that. And I'm going to actually change the color of that when I change it to purple. All right. So again, we have this function that is differentiable on this interval A to B. It has a point on the graph when x is equal to c, some point somewhere in between, where if you take the derivative at that point, it's going to be equal to this. Now keep in mind, f of b minus f of a over b minus a is going to be equal to this right here. So the slope of the line, the derivative at this point is going to be equal to essentially the slope between these 2 points, which is also referred to as the secant line. So this tangent line is going to be essentially equal to the secant line. You see they're parallel, they have the same slope. Okay? And so let me write some more verbiage down here. So in other words, there is a point on F and specifically P, where the slope of the tangent line, the blue line that I drew, is equal to the slope of the secant line. And hopefully I've illustrated that to you pretty well here. Okay. Is that something I want to write down? Okay, yeah. So basically the mean value theorem, it gives us information about a function from the function's derivative. Okay. So basically, if you know like the secant line between like the interval that of concern of the function that you're looking at, there's going to be a point on the actual curve where the tangent is equal to the secant. So watch this too. Here's another example. I didn't put it in my notes, but I want to put it here. Oh, I didn't mean to do that. Let's scroll on down. Say, for example, you got another graph that looks like so. Okay, let me make sure. I'm gonna do my best to draw this, but I'm just kind of drawing with this little tablet thing here, so we'll make it just make it happen. Okay, I want this line to be blue. It doesn't really matter. Okay, so let's say we have, okay, you got this point here, and this curve kind of goes up and down and up. It's not perfect, but you kind of get the idea. Okay, so once again, you got point A, you got point B. Now, the secant line, I'm gonna make this, the secant line is gonna look something like this because it's gonna be, f of B. Let me see, f of B minus f of A over B minus A. I'll keep all these lines purple. So watch this. If you notice, oops, why did that do like that? Okay. So there's going to be a point here where the slope is the same. There's also going to be a point, this doesn't go weird on me, here where the slope is the same. So let's label these. I'm going to label one of them. It's going to be P1. I'm going to label this P2. So this is the secant line. Each of these are tangent lines. So it's pretty intuitive that the secant line, and that's supposed to meet that point there. The secant line, the slope of that secant line is going to match the slope of the tangent line at two different points on this graph. Okay, points that are in between A and B, just based on the shape of the graph. Okay, so basically, again, just to restate the mean value theorem, it says if a function is differentiable on the interval AB, then there exists a number C between A and B such that the derivative is equal essentially to the slope of the tangent line. The derivative, which is like a slope of I meant to say secant line. The derivative, which is like a slope at a the slope of a tangent line is going to be equal to the slope of the secant line, f of b minus f of a over b minus a. Okay. Okay. So good. So in other words, if you can kind of take the slope of the secant line between 2 points or whatever, then it gives you an idea of where the slope of the tangent line is going to be. The derivative is going to be at least 1 point between A and B. Hopefully that makes sense. All right. So to finish this video off, let me give another um example that I wanted to give here. Let's see. Now this is going to be a little interesting to draw for sure, but we'll just kind of, again, try to make it happen. Say, for example, give me a second here while I do some more um drawing. Sorry for the wobbly line. So say, for example, we have something like this. Let's go back to red. Say, for example, we have a line. Okay, it goes up, down, up. Ooh, no, no, no. Why did it do that? Let's delete that. Hopefully it'll let me do it without too many issues. Then it goes up like that. Okay. Okay. Now, this is going to be um let me see, how do I want to do this? So this is supposed to correspond to this point here. It's not perfect, but you kind of get the idea. Let me see. 1, 2, 1, 2, 3, 4. So this is 4. This is 5. Okay. So the question says use the graph to estimate values of C that satisfy, satisfy the conclusion of I'm just going to do an abbreviation for mean value theorem on the interval 0, 8. And I didn't label those points yet, but they are as follows. This actually corresponds to x equals 8 right here. And then, of course, this corresponds to x equals 0. That's pretty obvious. Okay, so this is x is equal to 1. Let me see. 2, 3. Then you have 4, 5, 6, and then 7, 8. It's not perfect, but 4, 5, 6, 7, 8. All right. Now, so here's the thing. What we want to do is we want to find the slope of the secant line, which again, if you recall, is going to be between this point and this point. Okay, that's the where the secant line is. So f prime of c equals f of b minus f of a over b minus a. So f of b is going to be this is at 8, 5, and this is at 0. What was this? I'm sorry. 1, 2, 3, 4. Oops. This should be 4. Actually, let me redo this. I wrote some of these numbers wrong. So this is actually supposed to be at 0.6. This is 5. This was 4 right here. So sorry. So this is at 0, 4. Right? 1, 2, 3, 4, 5. Yeah. So sorry about that. Let me clean it up a little bit. So hopefully it's not confusing. Okay. So f of b is going to be f of 8. So that's going to be sorry, this I need to rewrite it. That's supposed to be rewritten as 6. That's going to be 6 minus f of a, which is going to be 4 over b minus a. So 8 minus 0. It's going to be equal to 2 over 8, which is equal to 1/4. Okay. So what do we want to do? We want to try to figure out spots where the slope is approximately the same thing. So, and again, mine is not really drawn to scale very well, but like you figure a slope like that, you're going to have a point somewhere. And I should have done a different color. Let's do blue again. So if this is the secant line, so that means the slope is 1/4. Then we're going to have a point somewhere over here. So like, maybe just before 1. So like 0.8. Then you're going to have a point. Okay, we're going down, down, down. Where else is so somewhere over here. So like just after 3. So we'll say maybe 3.2. Okay. And then you figure, so it goes up and then it kind of crests um again. So right around maybe here. So about 4-ish. I'll just say 4.1. Then you have it goes back down, then it does it again, maybe about here. So like just after 6. So maybe 6.3. Okay. So again, those, and you can kind of, if you have the graph like I do in my book here, you better see, kind of eyeball a little bit. But even based on the way that the slope, you can kind of eyeball how the slope would look between secant line and the way the curve is curvy, for lack of better words. You'll kind of be able to see a little bit better here in the book. But anyhow, this is how the mean value theorem works. So there's at least one point between the interval endpoints where the slope of the secant line is going to be equal to the slope of the tangent line. At least one, but as you see here, it's like 1, 2, 3, 4 different points. Okay. So that's how the mean value theorem works. It tells you that you're going to have at least one place where the secant line slope between those 2 points matches a tangent, like in other words, a derivative. Okay. Hopefully that's helpful. Future videos are gonna kind of like use this a little bit more, but hopefully this kind of like just opens your mind about how this particular calculus concept works. All right, thank y'all. Make sure you like, make sure you share, subscribe, and have a good one. Hey, thank you for watching this video. If you need math tutoring or you need SAT math help, look in the description to find out how you can sign up today. Also, don't forget to like, share, and subscribe so you stay in touch with Math Swap Tutoring on YouTube. Have a good one.